All right, guys, it's me, Miss Murphy, once again. And today we're going to be talking about a different type of exponential function, but it's still the same format called exponential growth and decay. So, with exponential growth and decay, you will be seeing this a lot, specifically in Math 3. So, you will be seeing this again. This is usually the type of function that I like to think of when I think about exponential functions. It's one of the functions that are usually used the most in real world aspects. So we first start with our I can statement, which is I can write an exponential growth or decay equation given a word problem. I can also identify the percentage of increase or decrease based on the equation. So again, these are very, very similar to what we've been doing the past 2 days with exponential functions. So it still kind of has to deal with how the graph is increasing and decreasing. A lot of the parts of it are pretty much the exact same, but typically you will see these in a more real world function. All right. Or real world problems. So let's look at the formulas for growth and decay. So for growth, the typical formula is f of t is equal to a times 1 plus r raised to the t power. Now, the a is similar to the a value in our previous lessons. So as you know, the a value typically represents the y-intercept. Well, now the a value is still our initial amount. So we're talking about the word problems. A is typically your initial amount. And that's when you're talking about either growth or decay. So if you notice, the only difference between growth and decay is that growth has a plus, decay has a minus. And we'll talk about in a second what that means. Now, R is the percent that you're growing or this percent that you're decaying. So we call that your growth dash. So we call that your growth dash decay rate. That is the actual percentage of which it's saying you are going to increase. So your R is your rate of growth dash decay. Now, in word problems, they will typically give this to you as a percentage. But when you plug it in for the R value, you have to convert the percent to a decimal. So typically they'll give it to you as a percent, but you've got to make sure you convert that percent to a decimal for either of these R's. And then lastly, we have our T value. And T, as we know for most of these, T usually means time. So how much time has passed? Now, another thing to notice about these equations is that if you look closely, the 1 plus R is our B value for rate of growth. The 1 minus R is our B value for decay. And if you think about it, growth means that the graph will increase. So that means that our growth factor, or our actual B value, will be greater than 1, which makes sense because we're adding 1 to whatever our percent rate is as a decimal. So that would give us a number greater than 1. Whereas decay is subtracting the rate from 1. So since decay typically means decrease, which means that our B value has to be between 0 and 1, or a fraction, or even a decimal, as long as it doesn't have a number in front of the decimal, that would also make sense. All right, so that's just something else to think about. So again, exponential growth and decay. Exponential growth is an increasing graph. So the graph increases. Your B value is equal to the 1 plus R, so the 1 plus your rate. And again, that also means that your B value will be greater than 1. So when you add these two together, that would give you a number greater than 1. Your A value, again, is your initial amount, or where you start at. It is also your y-intercept. And don't forget, T means time, and time relates to your x value. That would typically be your x value. And R, even though R is in it, it is not a part, it does not replace any variable that we are using previously. It is part of the formula to get your B value. Now with decay, so again, we're decreasing. So that means the graph is decreasing. Our B value comes from 1 minus R, which again, if we're subtracting a decimal from 1, that means we are going to get a smaller decimal that's going to be somewhere in fraction land. So it'll be between 0 and 1. And again, A is still equal to your initial amount, which is also your y-intercept if you're looking at it from a graph standpoint. And T is still your time. And remember, time is still your x value. So these are things to think about when you're talking about exponential growth and exponential decay. And typically in the word problems, they will tell you whether it's going to be growing or decreasing. They'll use that verbiage. However, sometimes they may show you a graph and you have to determine whether it's growing or decreasing. It just depends on what they give you in the context. So let's do some examples. So just to do some calculation practice, we're going to find the multiplier for each rate, or in this case, each rate for the exponential growth and decay. So we start at 1. And remember, we are talking about decimals converted to percent. So 1, we're talking about 1.0, which converted to a decimal would be 100%. So this is the same as 100%. Now, you add the R value if you have growth, and you subtract if you decay. Then you can divide the results by 100 to turn the rate into a decimal. So whatever percentage rate, so remember your percentage or your rate will typically be given to you as percentage. Take whatever the percentage is, divide it by 100, and that would give it to you as a decimal. So, first things first, we're going to go through these together and find our factors. So, it says rate, but in reality, we are finding the factor of exponential growth and decay because that would actually be our B value. When you hear factor, you're going to think your B value. So, first things first, we're talking about 12% growth. So that means that we're going to do something on the lines of 1 plus R because we're growing. So we're going to add our rate to it. Now, 12% is equal to our R. However, we want that in a decimal. So I'm going to divide 12 by 100 to get my R value. And you can do that in your calculator. So you can do 12 divided by 100, and that'll give you 0.12. So 0.12 is equal to my R value. I'm then going to take this value and plug it into the purple formula for R. So this then becomes 1 plus 0.12, which means our growth factor in this case is 1.12. So this would be our growth factor. So if you think about it, if you're growing, that means that you have the full amount that you started with and you're building up on it. So we have to have that 100% because we have 100% of the initial amount, and then every so often, depending on the timing, we increase by 12%. So we're adding on 12%, but we have to have that one there because we have to include the 100% of the initial amount that we started with. Now, on the other hand, we have exponential decay. So that means we're going to have the 1 minus R formula to give us our decay factor. So again, this 7% is our R value, but we want it as a decimal. So I'm going to do 7 divided by 100, and you can put that in your calculator. If you do, you should get 0.07. And you're going to stick that in for the R here. So that means you would have 1 plus 0, or minus, my bad, 1 minus 0.07. And again, you can put that in your calculator. So 1 minus 0.07, I get 0.93. So this would be 0.93. So when you think about decay, that means you're taking whatever your initial amount is and you're getting smaller. So when you're decaying by 7%, that means that for each step, you're only going to have 93% of the former amount left, and so on and so forth. Whereas with the growth from the first example, we would have 112% more as we go from the initial to the next as we build it. And again, we'll see some more when we build these examples. But if we convert these back to parentheses, that means we would have a factor of 112%. And that means here, this would be a decaying factor of 93%, which you may see occasionally. But typically, these will be the decimal answers will be what you want. So with these two, I'm going to go rather quickly. So we have our growth. So again, 1 plus R. This is our R value. So I'm going to do 4.5 divided by 100. So if you do that in your calculator, it should give you 0.045. Then I'm going to do 1 plus 0.045. So that will give me 1.045. So that would be my growth factor. And again, if we convert it back to a percentage, remember you just multiply by 100 to convert it back. This would be 104.5% growth. And then finally, our decay. So remember, decay, we have 1 minus r. This is our r value, but we need it as a decimal, so 8.4 divided by 100. Again, you can put that in your calculator, and if you do, you should get 0.084. Then we're going to plug it back in for r. So I have 1 minus 0.084. And I'm going to put that one in my calculator quickly because I don't know that one off the top of my head. So 1 minus 0.084, I get 0.916. So this will be 0.916. So that's our decay factor. And again, if we turn that back into a percentage, so multiply that decimal by 100, you get 91.6% decaying. So that's how you would calculate it. Calculate your B values for the exponential growth and decay functions if you had to build the functions on your own. You take whatever percentages, convert it to a decimal by dividing by 100, and then put it into the respective formula. Now, it's asking for the percent growth dash decay of the following functions. So now we're working backwards. So remember, your rates or your factors come from your B values. So all of this will come from your B value. However, we would have to figure out whether it's growth or decay. Now, the easiest way to determine whether it's a growth or decay, again, if your B value is greater than 1, it's a growth. And if your B value is between 0 and 1, it's a decay. And then we've used the respective formulas for each. So, first things first, we'll do letter A. So we're looking at our B value, which is right here. Now, judging from this being bigger than 1, we're going to say that this is a growth. So this is going to be a growth of some kind, which means that we're using the formula 1 plus r. So we do not know what r is, which would be our percent growth dash decay. So the way we would state this is we would basically work backwards. So we know 1 plus r is equal to 1.05. So we can subtract 1 from both sides to solve that equation. We would get r is equal to 0.05. Now, our question asked for a percent. So we need to convert this decimal to a percent by multiplying it by 100. And if we do that, we would get 5% growth. So this is a 5% growth. All right, same thing for letter B. Here's our B value. Since it is less than 1, we're assuming that it's a decay. So we're using 1 minus r. So again, you can set up a very quick equation. So 1 minus r is equal to 0.85. So I'm going to subtract the 1 to both sides. I would get negative r is equal to negative 0.15 or 0.15. Divide both sides by negative 1 to get rid of that negative. And r would equal 0.15. And then don't forget to multiply it by 100 to get that percent, which that percent would be 15%. Now, I'm going to leave C and D for you to try on your own. However, I will post the answers to it on your PDF version of this journal. So take a minute, try those on your own. Now, our next example actually has us looking at a word problem and figuring out what's going on. So the number of bacteria in a lab is increasing by 2.5% per minute. The experiment started with 200 bacteria. So first off, what is the growth or decay rate? So first off, we need to figure out if this is a growth or decay. And by the way, this is not rate. We want the factor. So again, this would be our B value. So we first need to figure out if this is a growth or decay. And we can figure that out by this word right here, increasing. Since it says increasing, that implies growth, which means we're using the 1 plus R. We also need to determine what our R value is, which is right here. It's the percent by which we are growing, or 2.5%. So that's my R value. Now, I need to convert that R value to a decimal. So do 2.5 divided by 100, and that means you would get 0.025 if you put that in your calculator. So if I put it into the growth formula, I would have 1 plus 0.025, which is just 1.025. And we can just leave it like that. This would be our growth factor. So that would also mean that this is our B value in our function. So in reality, you don't need to remember those complicated formulas at the beginning. If you just remember this part and then the 1 minus R, that's your B value. That's all you have to do to find your B value. Everything else is pretty much the exact same as what we've been doing the past 2 days. Now we got to write an exponential function that models the number of bacteria, y, as a function of time in minutes that has been growing by x. So, in other words, we are going to put this back into what we know about exponential functions, or y equals a times b raised to the x power, which, if you think about it, is the exact same as our exponential growth equation, which is y equals a times 1 plus r raised to the t value. The only difference is that the 1 plus r is replacing that b value. That's the only difference. And this isn't why it's f of t. All right, that's really the only difference. You just have to do one extra step to find the b value. So we're just going to plug in all the stuff that we know. So first off, we need to discern our A value. And remember, your A value is your starting amount, which if we go back to the original problem, that would be that they started with 200 bacteria. So A is equal to 200. Now our B value is the 1 plus R that we did in the previous question. So we already have that. And then we don't have a value for X or T, whichever way you want to put it. So we're just going to leave that as X. So our function is going to be Y is equal to 200 times 1.025 raised to the X power. And that would be our equation. Now, how many bacteria to the nearest whole number does the model predict after 1 hour of growth? So be very careful about this one. So to the nearest whole number, so that's what we're rounding to. How does our model predict how many bacteria will our model predict will be present after 1 hour of growth? Now be very careful because it says 1 hour. But recall that our formula is in minutes. So we got to not say 1 for X. We have to say 60 for X because there's 60 minutes in an hour. So that is what X is equal to. So that's our X value. So essentially we're going to take this 60, plug it in for X, put it in our calculator. So I have Y is equal to 200 times 1.025 raised to 60 power. I can put that fairly quickly in my calculator. So I have 200 times 1.025 all raised to the 60th power. And so I should get about 87.95. It asks us to round to the nearest whole number. So since this is a 9 in the decimal place and a 9 here, it will round up to be 880. So we will state that this is approximately 880 bacteria after an hour. So again, be very careful and watch the units that they give you because you have to make sure that your problem or the values that you plug into your equation is in the same units that you wrote the equation in. Since we wrote the equation of time in minutes, that means that even though it says hour here, we have to put the minute conversion in. So again, read your problems very, very, very carefully. All right, last one. So you just bought a new car for $48,000. Your car depreciates in value by 8.5% annually. So first off, we want to know what the growth or decay factor is. So again, that's your B value. Now, based off of what we know, we need to figure out if it's a growth or a decay. We can tell by this word depreciate. Since it says depreciates, that means we're decaying. So remember, if you've ever bought a car, it depreciates in value or loses value as soon as you drive it off the lot. So that's what depreciates means. It means you lose how much it's worth. So the price that it's worth goes down the longer you have it. Now, when they say annually, that just means once per year. So make sure you know that too. So once per year. So our factor will probably be in years. So again, make sure you know those words as well. So since we're doing a decay, that means we're using the 1 minus r formula to find that B value. So I'm first going to do 8.5 divided by 100. So I have my rate or my R value right here as a decimal. So this would be 0.085. Then I'm going to put it back into the formula. So 1 minus 0.085. And again, you can put that in your calculator. So I have 1 minus 0.085. And I get 0.915. So this would equal 0.915. And that would be my decaying factor, which is also, remember in our equation, my B value. Now we can write the exponential function that models the value of the car, y. So the value of the car, y, as a function of time and years, x. So we first need to figure out our A value, so where we started at. Well, it's basically what we bought the car for, which is $48,000. So our A value is equal to 48,000. So I would get y is equal to 48,000. We then need our B value, which we found to be 0.915. And we're going to raise it to the x power. And so this would be our function. And then finally, it wants us to know the value of our car after 6 years. So remember, 6 years, since we're talking about years, that means we're dealing with x. So that means x equals 6. So we're going to plug that 6 back in for x in our original function. So I'll get y is equal to 48,000, 0.915 raised to the 6th power. And you can just put that straight into your calculator. So I have 48,000 times 0.915, all raised to the 6th. Now, it's not a pretty number, but we're going to assume that they want us to round to the nearest dollar. So that means we're not going to have a decimal anymore. So we're going to round up to the nearest dollar. So since this decimal is a 7, this means that this will go up. So we're going to say our answer is $28,169. So y in this case would equal $28,169. So after 6 years, that's how much our brand new car is worth. So hopefully you guys understand this. If not, please feel free to come see me in 923 and ask questions, or you can shoot me an email. But it's very, very similar to what we've been doing the past couple days. There's really just one extra step. And I will post the key to the journal, the written key, as well in Canvas. Hope you guys have a great rest of your day.